Alright, in the previous video, we built our convolutional neural network to classify cats and dogs. The model achieved nearly 98% accuracy on the training set. However, the validation accuracy remained stuck at only around 73%. That big gap between training and validation performance tells us something important. Our model wasn't really learning to recognize cats and dogs. Instead, it was starting to memorize the training images. This problem is known as overfitting. So the question becomes how can we expose the model to more varied data without actually collecting thousands of new images? One of the simplest and most effective solutions is data augmentation, and that's exactly what we will focus on this video. We will begin by repeating the same data set preparation steps from the previous video. We will download the cats and dogs dataset from Kaggle website and organize them into training, validation, and test folders and get everything ready for training. So now let's import the libraries we will need. Alongside TensorFlow and Keras, we will use ImageDataGenerator, the core tool that makes data augmentation possible. So first, let's look at our directory structure. Our base directory is set to base dir equal to this address. Inside this folder, we have three main folders: terrain, validation, and test. Each of these folders further contains two subfolders: cats and dogs. This structure is important because it matches that flow from directory expects. The method will automatically assign labels based on the folder names. So we don't need to manually label anything. Before jumping to the code, let's first understand the core idea. Imagine you're trying to recognize your friend's face. Even if they tilt their head a little, move slightly to one side, or step closer to the camera, you still recognize them without any trouble. But a neural network doesn't have that natural ability. If it sees the exact same training image repeatedly, it may eventually memorize that specific image instead of learning the general characteristic of a cat or a dog. That's exactly what happened with our previous model. Data augmentation solves this problem by generating slightly modified versions of every training image. The key point is that the actual content doesn't change. It's still same cat or dog. We're only altering how the image appears, so the model is forced to learn more robust and general features. Now let's talk about how we actually implement data augmentation. We will use ImageDataGenerator, which comes with many parameters to control the types of transformations applied. Some of the key parameters we will use include rotation range. It randomly rotates the image within a specified degree range. For example, from 0 to 40 degrees, or with an high shift range for rotating the image horizontally and vertically, and so on. And there's also an important parameter called fill mode. This determines how to fill in missing pixels when transformations like rotations or shifting create empty areas in the image. For example, fill mode equal to nearest fills the empty pixel with the nearest existing pixel values. All of these transformations happen randomly during the each epoch. For example, rotation range means equal to 40 means the image will be rotated by a random angle between 0 to 40 degrees every time it's loaded. This randomness ensures the model sees different variations of the same image throughout training. To make this more concrete, let's actually see what data augmentation does to a single image. First, we will load an image using a Keras image model. We will pick one specific image to augment. In this case, a cat image from our training set. Next, we resize it to 150 by 150 pixels, which matches our model input size. Then we convert it into a NumPy array. Now, here, an important step, we need to reshape the array because our model expects batches of images. Even though we're only using one image, we need to add an extra dimension to represent the batch size. So we reshape it to 150, 150, and 3, where 1 is the batch size and 150 is the image size, and 3 represents the RGB channels. Finally, we use the flow command to generate batches of randomly transformed images. This method runs in an infinite loop, so we need to break out it after generating a few examples. When we display the results, we can see the same image with different variations: rotated, shifted, zoomed, or flipped. This demonstrates that in each epoch, our model will see different pixels arrays for the same image, effectively making the dataset more diverse. Now, look at the output, and every image is slightly different. So they all clearly the same cat. This is exactly the kind of diversity we want to model to learn from. So it generalizes better rather than memorizing exact copies. Now let's build our CNN. The architecture is identical to the one from the previous video. We're intentionally keeping the model unchanged so that if the results improves, we can be confident that the improvement comes from data augmentation, not from changing the network itself. This is where today's video gets interesting. The key difference is how we set up our data generations. Previously, our uh, training generate only normalized the image by rescaling pixel values to the range between 0 and 1. Now, we will also apply random transformations while loading the training images. So far, the training generator, we both rescale the data and specify augmentation parameters. But here's an important detail. We don't augment the validation data. Why? Because validation data should represent completely unseen real world images that we want to evaluate the model under normal conditions, not on artificially modified versions. So the validation generator only rescales the images. Next, we use flow from directory for both generators. This method automatically loads images from the specific directions, resize them to 150 by 150, and organize them into batches of, here we choose 32, and assign binary labels since we're doing binary classifications. Cats vs tags. We do this for both training and validation sets. Now we are ready to fit the model and run the training. So uh, everything else stay exactly the same. The only difference is how the training images are generated. Instead of showing the same image repeatedly, uh, every mini batch now contains slightly different versions of them. So let's train the network and compare the results. As we can see, data augmentation has effectively solved our overfitting problem. Let's visualize the results to understand this better. We will plot both the training and validation accuracy, as well as the training and validation loss over the epochs. When we look at the learning curves, we can see a clear improvement. The gap between training accuracy and validation accuracy is much smaller than before. Both curves follow a more similar trajectory. The validation accuracy has improved significantly compared to our previous model. That's a very good sign. It means that the model is learning features that generalize better to unseen images rather than simply memorizing the training set. Of course, data augmentation doesn't completely eliminate overfitting, but it significantly reduces and usually improve the model ability to generalize. That's why data augmentation has become one of the standard technicals in almost every computer vision project. So today we've learned that improving a neural network isn't always about making it deeper or adding more layers. Sometimes improving the quality and diversity of the training data has an even greater impact.